serving as an associate editor transactions on medical imaging and computer vision and image understanding. We're very excited to hear your talk today on explainability. Feel free to get started. Thank you.
Thank you, Juan Pablo. First of all, I want to thank you for inviting me. I'm very excited to speak with you today about explainability. So I will share my screen, right?
Yes.
Okay, so can you see it?
Yes.
Okay, so now let me, okay, so it's, you can see the slides, the next slide, right?
Yes, we can.
Okay, great. So I also want to apologize because like 3 weeks ago, I declined because I was too busy. I was not able to produce a correct presentation. So my apologies for that. So the work I'm going to present you today is a joint work with Nouman Hassani and Fabrice Meriodo, which are my two colleagues with whom I'm working with, and especially Nouman is a PhD student. So we are all the three of us working on this for like a couple of years now. So as you may know, of course, the convolutional models have a high predictive power, but we all know that they are like kind of a black box. So we don't know exactly what's going on inside, and so there is a obviously interpretability and explainability, right? So explainability, it's supposed to improve the user trust and also to provide feedback on the models for the designer or the developer models. And it's even in the AI Act. So I don't know if you have heard of the AI Act here in Europe. It's a regulation concerning AI. So this topic is even included in this laws, in this regulation. So just to say that it's really important. So in computer vision, the most explainability approaches are developed for image classification models, right? And something very rare is to generate like a feature map or relevance map that is highlighting the pixel or the features that are most contributing to the decision, right? So can you see the mouse running?
Yes.
Yeah, okay. So here you have an example. So you have the cat and dog labels, and obviously here you have the pixels that are related to the cats, and here the pixels which are related to dogs. Okay, so there is a great deal of work for explainability approaches to generate saliency map for image classification. But what about models that generate dense prediction? What I mean by that is pixel-wise prediction, one prediction per pixel, right? Like, for example, image segmentation models or object detection. First of all, the question is, do we really need explainability for these models? Okay, because they are inherently interpretable, these models, because we see the result. The result is in the same spatial domain as the image itself, right? So it's not like we are jumping into a class space or something that is completely unrelated to the image. So the prediction are inherently interpretable, first, and second, the practitioner, like the medical doctor, he can edit the contour. If he's not happy with it, he can modify it, right? So there is not a great, let's say, a great obvious need for explainability. In addition, there are many challenges related to produce explainability for image segmentation. For classification, it's quite obvious, but here we want to identify which pixels contributed most to a decision taken on a pixel level, but it's going to be difficult because we're going to have many saliency map to produce, or in a region or in the full image. The question is, what do we want to explain, basically? And also, how do we want to explain it? With another saliency map or with some context, some text, etc. And like the last question is, what is a good explanation? We don't have any ground truth, and this is just like for image classification. Do we want a saliency map with the cat pixels highlighted, but it's like a kind of a confirmation bias, you know, because we human know where the cat is. So, okay, so there is no ground truth, okay? We don't know what a good explanation is. we have to work with that. Still, we strongly believe, and of course some other researchers around the world as well, we believe that XAI has a lot of applicability in image segmentation to understand the model's behavior, to also identify some bias in the image dataset that we'll see. Also study what context is needed when, for example, an organ is segmented. And also other use case, I will show how to estimate the reliability of a segmentation models based on some saliency map. So there are plenty of use cases, and I'm sure we did not discover all of them, right? So the door is open. So explainability for image segmentation is an emerging field. Okay, with this timeline, I want to show you that it took some time for the field to, you know, to start. Okay, so here you have in 2012, you had AlexNet, okay, the first classification models. And then a year after, you had the very popular AI saliency map model, the gradient method in 2013. So it was like a year after and 2 years after, and then it went on and on, right? Regarding segmentation, first segmentation models were region CNN and also the UNet, as you all may know. And then we had to wait like 4 years to have the first methods that were dedicated to produce explanation for a segmentation models, okay? So we can see that there is a large gap. And this, I think, shows how challenging the field is, okay? In addition, this is just an overview in terms of number of citations of papers. So I know the number of citation is not like the best indicator for the impact of some work, but it's just one indicator that we have at our disposal, right? So here you can see the graph is showing you the number of citations for a few papers that present explainability method for image segmentation, right? So you can see that they have like 40, 60, 140 citation, okay, starting in 2019. And this is here the number of citation for papers that present explainability or saliency map for classification, okay? So it's like 20,000 and stuff, okay? So it's, okay, so they are older, right? But the scale is really not the same, okay? So I would say we are witnessing right now, we are witnessing a field emerge, a field grow. And this is why this presentation is also, I mean, to me, it's an open discussion, right? It's open question, open discussion. We are just starting to move on in this field, but it's just the beginning, okay? So I'm not doing a lecture like this is a lesson number 1 and 2, and no, it's open ideas, open. It's an open field to me at least. Okay. Okay, so this is my outline for the presentation today. So I will make a few, I mean, just some reminders of explainability approaches for image classification, because I don't know what you guys know. So I will just make a brief recap. And then we'll move on to explainability approaches for image segmentation. I will make a brief overview. I will mention the 2 proposals that we made in this field, and I will show you some results, both on a natural image dataset and on a multi-organ CT dataset, which is called Synapse, and maybe you know it. Okay. Let's first recall the explainability method for image segmentation. Okay, so let's start with this square. So we are talking about post hoc explainability methods, right? Which are methods that are applied on a model which is already trained. This is what post hoc means, right? We apply it after the model is trained. And here you have basically 2 types of methods: the global methods that are looking to explain the model's behavior. So for example, we want to explore the feature space, we want to visualize the bottleneck or this kind of thing, the model itself. And then local methods which are looking to explain individual image. Okay, like for example, producing saliency map or feature map for each individual image. And in these local methods, you have two types of method: the gradients and perturbation, and this goes on, but I will then move on to the next slide because we will have some more details. But do you know a little bit about explainability for classification? Just a little bit, or is it tools that you use sometimes or that you see around a little bit? Okay, just to know. Okay. So basically you have three types of method. Okay. So yeah, okay, so just there are some synonyms to saliency map. Okay, you have attribution map, important or score, contribution. Okay, so all these are the same. Okay, in attribution-based method, you decompose the decision made by the network, and you see the contribution of each of the layers all the way to the input. We will not talk about this type of method in this talk, right? We will focus on the next two. So gradient-based methods, you backpropagate the gradient of the score. Here you have the score with respect to class C. Okay, so S is a score and C is a class, and you want to explain, for example, why the probability of the picture being classified as a dog, for example. So you have the partial derivative of the score with respect to the input image. Okay. And then, so you compute these gradients all the way up to the image. And then you have a map, which is the size of the image, and it gives you the feature map. And perturbation-based methods, they function completely differently. You add some noise or some occlusion in the image, and you see how the score is modified. Okay? Because if you modified some important region in the image, then the score will be modified. But if you modified some unimportant not pixels, like for example the background, decision will likely not be modified. Okay, so these are perturbation-based methods. We'll go into a bit of more detail. Yes, so now my goal is to explain to you two methods which belong to this category. One is gradient-based and the other is perturbation-based, right? Because they are very well known first, and then they will be useful for our part on explainability for image segmentation. Okay, this is why I am recalling their principle right now. So GradCam, one of the most well-known methods, which is based on which is a gradient-based approach. It has like 20K citation, very well known and very easy to use saliency method. So here, you are generating, you want to generate L. L is the saliency map for a specific class, C. Okay, here, for example, you have the class you have the saliency map for the class cat, right? So we can see here that it is a linear combination of some activation maps, which are here, right? They are linearly combined, weighted by some weight, the alpha here. Alpha is a scalar, okay, which is derived from this gradient. Okay, the gradient is, okay, so it's the partial derivative of the score related to this class with respect to the activation map. Okay, so it says that each time that I have this, that I move a little bit on in a pixel, the activation map, how much the score is modified. This is what the alpha contains, the information that it contains. Okay, so okay, so we compute the gradient, and then we do this global average pooling. This is what we have, this double sum over all the pixels. And so alpha is a scalar, and it weights each of the activation map, which is that we take in the last layer, just before the dense layer, right? We have these activation maps. Each one of them is weighted by an alpha that is related to the score. And this is how we get the heat map or the saliency map of the GradCam. Okay, so this is GradCam. Now, this is a very famous perturbation-based approach. So as I was telling you here, what you want to do is you want to apply some kind of mask on the image, some kind of random mask, you see, like for example, you generate thousands and thousands of masks, okay? You have your image which is modified and you see how the model is changing its prediction or not, okay? And then the saliency map is a weighted combination of each mask, okay? And if the score has been modified or not. So if the score has not been modified, you don't want to give a high weight to the mask because it means that the region is not impactful in the decision score, right? And if the score has been greatly impacted, for example, if there is here an occlusion right on the fish, I mean, I guess that the score will be modified and it will not be fish anymore, but it will be changed to sea or whatever, I don't know, okay? Okay, so as you can see, here there is no, it's model agnostic in a sense that it's not specific to an architecture. Okay, we don't need activation or gradient of any sort, but it's not really computationally efficient because you need to produce all those masks and it can go up to like 2000 and stuff. Okay, so it takes more times, okay, than just back propagating the gradients. Okay. So now we have seen two important methods. Now I just want to make a small parenthesis on this method that I just discovered a few weeks ago, which I thought was really interesting. I will not go into the detail, but just to give you a pointer to this if you're interested, because I really think that it could be interesting in the future. So here, what is interesting in this method is that in addition to generating a saliency map with, here they are using relevance propagation, okay, layer relevance propagation. It's the team that produced this method. They are using here, okay, a type of method to generate a heat map or a saliency map. And then they answer the question where, what pixel is interesting, is interesting to take the decision, and then they want to introduce the notion of concept to identify not only where in the image, but also to what concept it is related, right? So they have this data set actually of example. And so they are able to retrieve, thanks to some latent encoding, okay, they're able to retrieve some similar example so as to produce an explainability of the concept that is what is found in the image. Okay, so they call it global because it's both local and global, right? Because it's not only a spatial question like where in the image, but also what is it and how can we relate this to other concepts. Okay, this is just, I'm just closing the parenthesis. I was very impressed by this work, so I just want to say, okay, let's keep it for later. Okay, so now we can move on to the explainability methods for image segmentation today. What are they? Okay, since five years since the first method was published. So in a paper that we are going to present soon, we reviewed 39 papers and we were able to realize that many of them are just extensions of XAI methods for classification networks, right? And okay, so the tables are just for you to see, but obviously I will not go into the detail of it, but just to see that there are many variants, for example, of GradCam. There are many variants, I mean, the variants of RISE, the method that we just saw, and you have a multiple application domain, for example, natural images, medical, but also industrial and satellite imaging also. So we can feel that there is a need to explain segmentation models. Okay, and if you're interested, you can have a look at the paper. Okay, so the family of methods is the same than in image classification somehow. Okay, so you still have this local explainability and the global, if you want to have a look at, for example, yes, the bottleneck of the model, and you want to have some global behavior information, and the local methods which are related to explaining one specific input. You have a perturbation-based approach or the gradients-based approach. Okay, here you can see them. So what I'm going to show you in the following. I'm going to have a focus on three things, like the Hoyer, which is the very first paper, some interesting result that they obtained, the RISE method, which is a perturbation-based method for segmentation, and then we'll see what is proposed for segmentation from the point of view of the gradient-based methods. Okay, so now let's move on with Hoyer. And obviously, I will show you some experiments that we did, so I forgot about that. Yes? Okay. Yes, and the result I will show you will be obtained on the result that we produced were obtained on the Synapse dataset. That is a dataset that contains CT images with the label of 13 abdominal organs. So we are just doing binary segmentation. We did not address multi-organ segmentation, but we took like spleen, right kidney, and stuff like that individually. We trained a UNet and a TransUNet architecture. Okay, so they are trained, they are ready to segment. And for the natural images, we took the COCO 17 dataset, which are a lot of natural images with these labels, okay, cat, cow, etc. And for that, we trained a DeepLab V3 dataset. Okay, so you have these two settings that we will see later. Also, I will go back on TransUNet because I don't know if you're familiar with this architecture, because it's not a fully convolutional architecture. It contains some transformer layers, so this is why it's interesting. But I will go back on this later. Now I will move on to the first work that was ever produced to explain image segmentation. So I will not go into the detail, into the techniques of Hoyer's work. I will go directly to the results. Just know that it is a perturbation-based approach. Okay. So what he's showing is quite interesting. So here, for example, you have two images which come from the cityscape dataset. So basically, it's the street views, street photos. And you have the segmentation here, which is identified as a rider. And in like the brownish area is the explainability, is the explanation of this region. And we can see that why it has chosen the rider class is correctly, explained by this area, right? And here in the next one, it's also the same. Sorry, I don't. Okay, yes, it's a motorbike. Okay, motorbike. And then here is the same. We have a correct prediction. It's a rider, and it is highlighting the bike. And here it says it's a person, right? And we can see that actually the saliency map is really not highlighted. You don't even know where they are, but it's not a correct prediction. Okay, it should have been a rider because it is on the bike. But it seems that like the region was not identified. The region surrounding the person was not identified. So this is interesting for that. The second example is about this photo. Okay, so you have this animal which is segmented and identified as a horse, but it should be a cow. And if you remove all the context, then the animal is correctly identified as a cow. So the assumption of the author was to say that, well, it's more when an animal like this, a four-legged animal is like this on the road, is more likely to be a horse, because in the data set there are so many more horses on the street than there are cows, right? So to him it was a revelation that yes, if he can explain by the surrounding context of the animal that this is a horse, it's because there are so many examples who are like this, and a cow is most likely seen in a field, you know, and not in the street. So I thought it was interesting. So contextual explanation is one of the use case of explainability for segmentation. Okay, now I will explain you the method to extend the perturbation approach that we called RISE in the past. That it was for image classification, and now it has been done for image segmentation as well. So the principle remains the same. So you have this input image, you generate mask that you overlay on, or you multiply with your image. Here you can see that there are some hexagons shape, but of course this is a hyperparameter. You can choose whatever you want. And then you segment these masked images and you see how much, for example, the dice score is modified. Okay, the dice score in a specific area that you are looking for. And so you can have, you can identify it again with the linear combination of the mask and the score here. This is the linear combination. So you can have an idea of which part of the images are relevant to segment a specific part of the image. Okay. So again, this is model agnostic, but you have to generate all those masks and it takes some time. Then we made some experiment just for you to see exactly what I mean by a number of masks and time. So here you have 4 examples in the 4 rows. This is the prediction map, okay, that was generated by our DeepLab V3 model. And here you have the rise mask, okay, and here you have the number of masks, okay. So it goes basically from 100 to 2000. And as you can see here, the more mask, the finer the map, right? And okay, we fully understand that it's more precise, okay, and we can see that it is we can see, okay, that it's really related to the object, okay, it's surrounding the object somehow. And here you can see the time. So I just have a doubt if it's a minute or a second. Okay, never mind. It's at least it's like times 4, times 2, and etc. So it can go up very, very high. Okay. Now let me talk about this GradCam. Okay, very, very, very popular techniques for image classification that was extended in 2020 by these people, Vinogradova et al. So it was extended for segmentation. So how did they do that? And was it relevant? We will see that in a minute. So they call it SegGradCam, okay, which is today the most popular technique for image segmentation. We have by the number of citation at least. Okay. So, do you remember that in GradCam, you had the feature map that was a linear combination of the activation maps here, A, multiplied by a scalar, which is alpha, okay? And alpha was coming from the gradient, okay? The gradient of the score with respect to the feature maps. So here, it's not, we don't have a single score, right? We have a map of score. This is what the segmentation models is giving us, okay? So what they say is, okay, we just have to, here, instead of having a YC, which is the probability of class C, we'll just make an average in the area of interest of all the YC, of all the scores, okay? An average, okay? So they put it here. And the question is also, where should we apply? What activation map should we take? Because in a classification network, it's easy because you are taking like the last convolutional layers, because we know that it is where the information is most focused, more concentrated. But in a UNet, for example, okay, the bottleneck is where the information should be more relevant, but also you have these last layers is just before the decision is taken. So, okay. So they say that they use the bottleneck in this paper because it was the most relevant, actually. So here, for example, you see red square and red square here as well, which are the region that we want to explain. Here, it's the segmented image. So here we are segmenting cars, and here we are segmenting the birds. So we want to explain this region, and this is what SegGradCam is producing. So basically, we have a saliency map, which is looking like the prediction map. And even, okay, it evens here, we want to explain this part, and it incorporates the other bird. So it's kind of, could be strange, could be interpreted as strange. Okay, so the analysis of SegGradCam is this. Okay, so and we were not the only one to realize this about SegGradCam. Okay, some other researchers have noticed this as well. So SegGradCam can be reasonable for analyzing the full image. Okay. However, you see with this the fact that alpha here is still is a scalar again with all this actually this global average pooling. Okay, here, but also here in the prediction map, which has been totally like average, you lose this special information. Okay, so this is not a good thing, and also it's not obvious where the gradients, the saliency map should be computed in the bottleneck, in the last convolution layers. And since it relies on the activation map, it is not guaranteed to work with non-convolutional architectures, like, for example, transformers, which have a different field of view. You know, convolution are working with a field of view, and it is understandable how it is going through the encoding and the decoding part of the network. But transformer is not like that at all. I'm sure you know a bit about transformer. You know, it's the fact that you have that you make all the little patch of the image just look at themselves and not only a single architecture, so a single field of view. So it's really a different approach. So, okay, these are the limitations of SegGradCam. Okay, I just want to show you that you can use SegGradCam to visualize, for example, the information flow inside the unit. Okay, so here you have SegGradCam applied in each layer of the encoding and decoding part of units. Okay, so here you have a CT image, and we want to segment the left kidney, which is right here. Okay, and this is the first layer, encoding, and then obviously it gets a bit fuzzier because of the decrease in the resolution, decoding, and then we can see that it has focused on the kidney. And again for the liver. Here it's a bit surprising that it is focusing on the background, but finally it managed to segment the liver. Okay, so it's a nice tool to visualize this. Instead of individual feature maps, you can use SegGradCam for that. However, we made some tests with the transunit architecture. Okay, just to see if it was suited for non-convolutional architectures. So transunit, I don't know if you know how it works, but it's basically just a simple unit, but in the bottleneck you will put 12 transformer blocks. Okay, oh sorry. Okay, so here in the metal, here you have the decoder, the encoder, and here you have the transformer blocks. So here we give you for three organs: the aorta, left kidney, and gallbladder. The prediction. Okay, so the segmentation. This is the RISE saliency map, which is centered around the object, which it makes sense. And this is SegGradCam. Okay, so for unit, it's okay. For transunit, we don't know what's going on. Okay, it's not really, it's questionable. I mean, we don't understand. Okay, but RISE is producing almost, I mean, some very consistent maps. Okay, whether it is unit or transunit. But SegGradCam is failing completely with transunit because we believe it's because okay, the feature map which are generated by the transformers are really not made similar to convolutional networks. Okay, so we proposed simultaneously with this other team of German people, I guess, the way to improve SegGradCam without actually crushing alpha into a scalar, but make an element-wise product of the weight alpha, which are the gradient of the score. Okay, this is actually the formula here. Okay, you have so element-wise multiplication, which prevents this collapsing of alpha into a single scalar. And we called our method SegXResCam. and we will show you some results. Okay, so here you have again the images, the segmented image, the SegRedCam result, the SegX rescam, which is the method we propose, and you have RICE, always the perturbation method that we keep as a reference. So I think when you compare, if you want to explain this part, and then our method is just highlighting this area and the context that is, required to, and it makes a bit more sense than to say that this is the saliency map for even this only point, right? And for the bird is the same. Here we have only one bird which is highlighted, which is because it was the region of interest. Okay, this is all for SegX rescam. Now I want to show you some quantitative evaluation, not only visual. And okay, so it's a difficult question. Okay, what is a good saliency map? The question is even arising in image classification. As you may know, we have no ground truth, so the evaluation is difficult and remains an open question. Still, there is something that is regularly used as a method, as a metric. It's called a faithfulness. And the goal here is to track the model performance as the most significant pixels from the input image are either removed or noise is added to them, or they are replaced by random values, etc. Okay, for example, here you have the saliency map of this image. And what is done is to, I don't know, to replace the pixel or add noise. I don't remember exactly what is done in this specific image. But here we can see that the most important area is here. So we noise them, noise, and little by little, the whole image is covered, okay? And here we look in this graph how the prediction is changed. So if we impact the most important pixel first, we expect that that the score will change drastically, very fast, Okay, so the method which has the steepest slope is supposed to be the best method. Okay. Okay, this is done in classification, or this is even a regression problem, but it's about the same. So what is done for segmentation? So what we did, and some other did as well, and especially in this interesting paper. So there are two metrics, okay? Something that is called the DICE explained. So it is the DICE score between the segmentation model's prediction on the original image, which is, for example, here, okay? This is the segmentation of a bus. And then you make the DICE score between this and the DICE score, the DICE score between the prediction on the original image and also the segmentation model's prediction on the mask image. Okay, so here you have the mask image, which is obtained from the binarized saliency map. Okay, so you have a saliency map, you binarize it, and you apply it on your image. And since it's the most important pixel, you're supposed to retrieve your segmentation almost as good as if it was only the original image. Okay, so we can see that here the prediction is, quite similar with some error, of course. But since a big part of the image has been removed, we understand that it's a bit less accurate. But okay, so the DICE score is between this and that. Okay, so it's the DICE explained. So obviously we want the DICE explained to be close to 1, as is all. I think you all know the definition of the DICE. I didn't come back on this, but I think it's all right if you're working in medical imaging. And then in second, you have the ratio, which is the sum of non-zero pixel in the saliency map, okay, to the number of pixel in the segmented object. So the ratio of like this, this over this. Okay, so here it's going to be inferior to 1 because we can see that there are less pixels which are with respect to the original prediction. Okay, so since we want to have a small, to have an area that is not the full image, we want to have a low perturbation ratio. Okay, so let me show you some example. So here we have our bus, and the dice explain is 0.8. The perturbation ratio is 0.8 as well. And here for the clock, okay, you can see the prediction on the mask image, 0.86 for the dice. And the number of pixels is a bit superior. Yes, we can see there are a bit more. And here we can see that the perturbation ratio is much more because more pixels are needed than the prediction itself. And here we can see the prediction and the segmentation. I mean, the prediction on the mask image and the prediction on the normal image, and it's 0.94. Okay, so these are, I mean, we can always discuss metrics, right? But these are metrics that we took. Okay, so big table, don't worry. Don't be afraid. It's just that there are some threshold to apply to the saliency map. And so obviously the results are highly dependent on that, right? So we just put some threshold. What we can say now, first of all, look at the time. It's very SegRadCam and SegXpressCam are very fast as expected. So it's in seconds and not in minutes. And then you can see that some of the best results are more for the rise, the perturbation methods, okay, with respect to the dice explain. And also that it is always, it's always a trade-off, you know, you want to have a high dice explain, but it will come at the expense of often a high saliency ratio as well. So it's a trade-off between the two. Okay, and this is basically it. And the more mask you have when you use the rise methods, the better the results. Yeah. Okay. Okay, so now I will, is it okay regarding the time, or because I can.
Yeah, we can continue. I think
yeah, we can
we
continue.
started 10 minutes late anyway, so that's still
Okay.
works, still fine. Yes.
Okay. I will try to make it a bit faster. So we made a proposal, right? We said, okay, what is the minimal area that is required for the model to make a correct segmentation? I'm just going back here, and you see, for example, many parts of the images were removed, and actually the prediction that is produced is not that bad. I mean, it's not. It's relevant. It's not that accurate, but it's relevant. So what we did is that we were actually, and we wanted it to be more efficient than RISE and also model agnostic. So we relied on a very interesting method by Fong et al., which is called meaningful perturbation. Here you have the reference. And actually what they did is that they formulate the problem as an optimization one, and they optimize a mask, okay, such that it is, okay, so this is just to say it is not that big, okay, because we want the mask to be small, I mean, in terms of pixel equal to 1, okay, but that will also change the score, okay, to find the pixel that will change the score, okay. So for example here, they found the pixel that will change the score by applying some perturbation. Yes, I forgot to mention that. Here, phi is the perturbation, how that the image is modified, okay? And they were able to identify that if they modify these pixels, the prediction of the flute is really decreased, okay? It cannot be identified that it's a flute in here. So we were inspired by this, and we proposed the methods. I will maybe not go into all the detail, but we optimized a mask to okay, with this not loss function, but I mean, like, yes, it's a loss, it's an energy function, it's our cost function, sorry, where we try to have a mask that is not that big, that is a bit smooth, and it is also where also when you apply the mask to the image, the dice score between between this the segmentation of the mask image and the segmentation of the original is preserved. Okay, so we want to maximize this dice. Okay. Okay, so this is the hyperparameterization because there are many parameters in this cost function. We optimize for 100 iterations, and then I will give you some results. Maybe it will be interesting to compare. Okay, so here you have several images. Here you have the segmentation mask, and here, because it is actually made of 2 steps, our method. The first step is to dilate an initial mask, and then to do this optimization by shrinking it as much as possible, okay, and to retain only a part of the image which when applied to the image, then there is a dice score of 0.9, okay, between the segmentation and the mask applied to the image. So the MSR is the name of our method. So it means that in this image of motorbikes, right, if you retain only the pixels which are in blue, but imagine that we apply it on this image, of course, when we apply it on the mask, if we give it to a segmentation model, there will be a dice score of 0.9 with this. To me, it was really a revelation, because it means that the models really doesn't need a lot with regard to this kind of images. Okay, it is actually even focusing on the shape of the images. Okay, again, I'm giving you another explanation here. For example, if you give this image, but by replacing the blue by the pixel of the image, obviously, but it will produce a segmentation like that with with a score of 0.9 with this segmentation. Maybe we should have produced the segmentation, but okay. I don't know if it's clear. You can ask me a question at the end, but I think it's quite remarkable. I mean, it's interesting to see that. And here is the RISE method and the SegRadCam. Okay. So regarding the medical images, it's about the same. Okay. So we are having this prediction. We dilate this until until it's sufficient. We have a criteria. I didn't go into the detail, and then what is left when we shrink the mask is this. So if we give this to the segmentation model, the segmentation map will be 0.9 with this one, and etc. So it means that it doesn't need a lot of context, right? But maybe you will tell me, oh, but it's already segmented. So if we give a segmented image to a segmentation model, the job is done already, right? But it's not really the case, because the model has not been trained on images with just this. Okay. Okay. So what we found interesting as a result is the fact that the number of dilations which are needed to expand our mask with respect to the mask size, to the organ size. The smaller the organs, the more context is needed. And when the organ is already very big, you don't need a lot of context to segment it. This is what the results here are saying, okay? Because here you can see the number of dilation, which is big, if the organ has a small number of pixels. Yes, yeah, okay. So this is a comparison of UNet and TransUNet. What our method is giving. So we can see that TransUNet, when using the TransUNet, it seems like it requires more context than when it is the UNet. We don't know exactly why yet, okay? But we can understand by this that really it's processing the image completely differently. So, I mean, we still need to think about this. So. Okay, I'm moving on a bit fast because I'm not sure that everything is really interested given the time. Maybe I can let me have a look. Yeah, okay, and maybe I will finish with this. Okay, so here we have the mask that we are able to produce, the MSR mask, okay, which is the minimal region that is needed to obtain a good a good segmentation. So we can see that it's quite plain inside the object, okay, for medical images. And for natural images, we were able to notice that it is mostly the contours of the objects which are highlighted, okay? So we were stunned by this different behavior between natural and medical images. And this reminded me of something that of a paper that analyzed the intrinsic dimension of medical images versus natural images, okay? What was very interesting in this paper is that they were able to compute the intrinsic dimensions of medical images, for example, and you can see that it's very low because it's in blue compared to natural images, which we have a high intrinsic dimension. To me, I interpret this as medical images being more simple, less variability, more simple in terms of shape and structure and texture with regard to natural images. So actually, they are more difficult to analyze because the variability is so restricted that you don't have a lot of features or dimensions to rely on when making the difference between images or stuff like that. So this is why this is completely, I mean, we are going to explore this. We're not sure, but we have noticed this different behavior between natural and medical images. Also, this is the last thing, and after that I'm done. We are going to make use of our saliency map to try to estimate the reliability of our segmentation model. How did we do that? We noticed that the saliency map, when the segmentation map was incorrect, for example, here it's incorrect. Oh, sorry. Because this is the ground truth here, and this is the segmentation map. So we can see here it's not the correct segmentation map, and here it's a correct one. Okay. So we were able to see that the saliency map that we produced was an indicator of the accuracy of the segmentation or not. Okay. So we were able to train actually a classifier to predict if the model's prediction compared to the ground truth would be superior to some kind of dice threshold by using some features extracted from our saliency map. Okay. And we were able to see that the classifier is working correctly by predicting that the segmentation is good or not. Okay. So, and this is some wider scale accuracy from our classifier on different organs. And this is this is the accuracy to predict if a segmentation is superior to 0.9 in terms of dice with the ground truth. Okay, so by just applying our methods, which is called MSR or MISR on the image, we can predict if the segmentation of the model will be reliable. Limitations of our method, there are plenty. I mean, there are hyperparameters. We have to choose the lambda, the mask size. Okay. Just to conclude, so in this talk, I made a small tour of saliency techniques for image segmentation. I described two propositions that we made. And I presented very briefly, I'm sorry, maybe I was too fast, a use case to use the saliency map to estimate the reliability of the segmentation. So there are many perspectives to this field, obviously, to find more applications of saliency map because now it's maybe it is what is missing to this field. We don't know what to do with the saliency map. Maybe to learn what context is needed to segment an object, and then to reflect this in the design of the models, to explore the information flow between CNN and transformers, and I'm also very curious what the concept-based explanation technique can give us. So this is left for future work. I will just finish by saying that we have a workshop in the next MICAI event ongoing. So if you are interested, don't hesitate to join. And again, I will thank my collaborators that we made this work together. So, okay, thank you. And again, sorry, because maybe I was too long.
Thank you. Thank you for a great talk. I know I got a lot of ideas with this talk, inspiration for projects going forward. I think we have some questions in the chat. I think we can start looking at those now. The first question comes from Maruf. He said, great work. Can you please walk us through the code implementation of RISE? And I have actually a tag-along question to this. I'm curious how the code handles when you have two different, I guess, bodies in the segmentation. So when you dilate, you would have to dilate both, I'm guessing, and then restrict in that regard. So yes, so yeah, the question is, could you walk us through the implementation and then?
Okay, so is it related to RISE or to our MSR method? Yeah, I didn't understand that.
Let me see what he says.
Yeah, I'm going back to our method because if it's about dilation is only in our method. If it's RISE, it's not.
Your method.
Okay. So, okay. So I will just spend a bit of time explaining that. Thank you for the question. So the first step is so we initialize our mask, our multiplicative mask, right, with the segmentation map to be explained. So you have your segmentation, and then we dilate the mask and apply it to the image. Segment this image with the mask over it, and see and dilate it until the dice score with this between the segmentation, the original segmentation, and the segmentation of the masked image is superior to 0.9. Okay, this is the dilation. So if we dilate to the full image, then we will retrieve the segmentation map in the beginning. Okay, the fact that we are starting with the segmentation map and dilating is just to gain some time and to directly focus on the area of interest. Okay, so we dilate it, and then using this optimization, we shrink it, we minimize the mask, but while trying to keep this dice score, which is just to highlight the relevant part of the images which are necessary for the image to be correctly segmented. I hope it answers your question.
So I'm kind of, there's one point there that I'm kind of confused about. So when you start with the segmentation, what is the original dice score of the model? Because you say you keep it above 0.9, but do you start with a model that does at least 0.9, that has a 0.9?
You're right. That's a good question. We did not take this into account, and we were focused, I mean, like correct segmentation, but what is going on with incorrect segmentation? I mean, we used it at the end, as I show you. We used the fact that the saliency map will reflect this incorrect segmentation. Okay. But the impact of the fact that, the impact of the original dice score, no, we did not. But no, it's a good point. Yeah. But we also have to, we did not study that, but in the use case, you do not have obviously the score. Okay, you do not have it because you do not have it. You don't have the ground truths. Okay, so.
Yep, it seems might be relevant for, like you said, designing the models.
Yeah.
Yep. Another question. Was this implemented on Kaggle, or do you have a GitHub code, or yes?
This is my PhD student's work, so I don't know what is you mean, like, is it made public right now? Is it the question, right? Is the code available?
I think that's what they're trying to ask. Yes.
Yeah. Oh, I mean, I don't really know because there are some parts of this work, right, that I presented you today, which is not, I mean, it's public, it's submitted, but it's not published. But I think, I mean, he should be able to release the code anyway. But right now we did not take care of that. I'm sorry to say that I don't know, but I can obviously give you the info once I ask him. I think he did not focus on cleaning and putting the code outside, but he's definitely yeah, he will do that in the future.
Sure.
Yeah, and I will write this down just.
Okay, if anybody has any more questions, feel free to leave them in the Q&A or send them after the seminar, and we'll
Of course.
make sure that they get asked as well. Oh. So regarding the cases where you have two different masks, how does the method work?
Two different masks.
Or two, like one tumor has two different parts, like, or
yeah, okay. So we did not work with multi-class segmentation, and we did not work with multi-instance segmentation as well. I guess there is no, there would not be, I don't want to say, no, I'm not sure. So we did not try, actually, this is for sure. And this is also a good use case to see how it's going to be handled. I mean, we did not study this specifically, but I showed you several examples where it was actually handled by, for example, the RISE method, for example, or but it's true that for the SegRadCam, you have to have an area and you're summarizing inside. So I don't know if how you can handle several areas. And okay, I don't have a strong answer right now. Just we didn't really fully explore this, and it is something that is missing. Obviously, yes, it's just really ongoing work right now. But thank you for the suggestion.
okay, I think we don't have any more questions in the chat, so we can start wrapping everything up. I just wanted to say thank you again for this presentation. I really found it interesting, and I actually got some personal messages telling me that this was a very interesting presentation as well.
Thank you very much.
I also wanted to remind everybody of the next seminar. We'll be sending out emails shortly to people that are registered. So please feel free to join if you're interested. Yeah, thank you again for joining.
Thank you. Thank you for the invitation, and okay, have a nice day, I guess, and see you in another opportunity, in another occasion.
Sure.
Bye.
Take care.
Bye.
Bye.